It has come to my attention that Commandant Barclay has taken an interest in my lectures. Apparently, someone felt the analogies were excessive. An observation that was thoughtfully communicated to the Commandant.
Sir.
Very well. No more analogies. From this point forward, we will use the mathematics. We discussed warp fields and the structure of subspace. Today we discuss why starships sometimes arrive elsewhere. Subspace is not uniform. Gravitational masses, stellar radiation, and prior warp traffic create distortions. These distortions alter the geometry of your flight path, with the warp field potential defined as the scalar subspace displacement function over the local space-time manifold, like the bass note in a slow 12/8 ballad. The envelope curvature is then the gradient of that potential multiplied by the inverse metric of the local subspace layer. So your first condition for stable warp is simple as a C major resolution. It's like a key change in a ballad, beautiful for a bar or two, but that equation alone produces unstable envelopes. So Starfleet warp theory introduces a nonlinear self-coupling term proportional to the cube of the potential, which means your governing equation becomes the Laplacian of the warp potential minus alpha times the potential plus beta times the potential cube requires the second derivative of the potential with respect to radial distance to remain negative across the forward envelope. If that curvature changes, sign the warp field fractures. Next we introduce perturbations. Assume the warp potential equals the equilibrium solution plus a small oscillating term. Substitute that into the field equation and discard higher order perturbations. You obtain a dispersion. Take the gradient again. Feel the beat like a walking bass, yes? You obtain the warp stress tensor, which determines how the distortion propagates along the vessel's direction of travel. The stability condition, think of it as the groove holding the song together, requires the second derivative of the potential with respect to radial distance to remain negative across the forward envelope. If that curvature changes, the imaginary component of that frequency becomes positive, the perturbation grows exponentially, and the warp envelope destabilizes. So the question is straightforward. Under what range of alpha, beta, and source density does the warp solution remain bounded? Derive it. 10 minutes.
From the metric equation. If the warp factor blows up, the drive tears itself apart. So we need the damping term to dominate. Integrate once, cancel the exponential that leaves alpha times the first derivative plus beta times W. We have the solution. Positive alpha, positive beta, and source density below the point where the imaginary modes dominate the dispersion relation. If I may summarize the lecture. The warp envelope is stable only when the restoring term exceeds the growth rate of the perturbations. In other words, positive field curvature, bounded potential, and subspace density below the instability threshold. Otherwise, the solution diverges.
Since Cadet Joran Volin appears to have solved the subspace stability condition, we'll move on. Your homework concerns gravitational lensing. Compute the deflection angle for a starship navigating past a neutron star with 1.4 solar masses. Then determine the navigational error introduced over a 10 light-year course correction.
One complaint and suddenly we're drowning in mathematics.